Hi, everyone. Now that we have our basic 10 properties, we can talk about what it's for. So we need those 10 properties to define linear combinations. So just to notice that if you have -1 times v, that's equal to the additive inverse of v. And because of that, we can define unambiguously what we mean by vector subtraction. U minus v means u plus the additive inverse of v, or literally u plus -1 times v. But then also, since we have associativity, u plus v plus w, we don't need to use parentheses because with associativity, we're allowed to do the addition in any order. We're guaranteed to get the same thing. So because of that, if you give me a bunch of vectors and a bunch of scalars, we can then just form this object called a linear combination. Now that we have that, we then talk about vector spaces that are inside other vector spaces, which we call back then, and we called them subspaces. So a subset S of a vector space is called a subspace if it's also a vector space, but using the inherited vector addition and scalar multiplication operations of V. Now, before we always worked in Rn, so going to something smaller wasn't a big deal because, well, you're just looking at the same vectors. So intuitively, you were already using the same operations anyway. But it's really neat to note that if you inherit all the properties from V for vector addition and scalar multiplication, then actually 8 of the properties are instantly true. Because if they're true in the big set, of course, they're true in the small set. Like, for example, if you take 2 vectors in the small set, you might want to know, can you add them in either order and get the same answer? Well, yeah, because if they're in the small set, they're in the big set where we know that's a vector space. So that number, that second property, comes for free. In fact, the only ones that don't are the 2 closure axioms. So because of that, we have this nice little theorem. If you ever want to prove that something's a subspace and therefore is a vector space using certain inherited operations, you only need to show 3 things. You have to show that the set is not empty. You have to show that it's closed under vector addition. You have to show it's closed under scalar multiplication. I'll do a whole bunch of examples so you can see. So here, look at the set of all polynomials. So we'll call that P. P then is a subset of F. Why? Well, it's pretty obvious. All you gotta do is just notice that the set of polynomials is not empty. There's at least one polynomial. And if you take any 2 polynomials and add them together, you get some polynomial. If you take some polynomial and take a scalar multiple of it, you get some polynomial. So it has the 3 things we need to be called a subspace. And as it's a subspace, it's a vector space. So we now know the set of polynomials is a vector space under normal function addition and scalar multiplication. If you look at the set of all n by n matrices, it's actually a subspace of m n by n. Why? Let's just say W is going to be the set of all n by n symmetric matrices for a fixed n. So they're all the same size. That way, vector addition makes sense. Notice that it's obviously not empty. Every n by n matrix, there is at least one that's symmetric. You just make everything 1. All the entries in the matrix may be 1. And then obviously now it's symmetric. If you take 2 matrices that are in that set and let C be any scalar, then instantly we know then that A and B have to be symmetric because that's the definition to be in W. So A transpose is equal to A and B transpose is equal to B. But then that means automatically that if you take the 2 matrices and add them and then take its transpose, one of the properties of transpose is that transpose distributes through matrix addition. So you get A transpose times B transpose. But A and B are symmetric, so that means that's A plus B. So A plus B transpose is A plus B. That's the definition to be symmetric. So A plus B is symmetric and is therefore in the set of all n by n symmetric matrices. Similarly, if you just take that scalar multiplied by A and then take the transpose, the scalar comes out, you would have the scalar times A transpose, but A transpose is A because A is symmetric. So that shows then that C times A is also symmetric and is therefore in W. Those are the 3 properties I need to show. So then this particular set of n by n symmetric matrices is a subspace of the vector space M sub n by n. and is therefore itself a vector space using those normal matrix addition rules and normal matrix scalar multiplication. Now there's so many, oh my God, there's so many other examples we could do. That's what makes this subject so interesting. This is that everything, almost a lot of stuff that we do are actually vector spaces, and we can think of the concepts in terms of linear algebra. Instead of proving them all, I think I'm just going to give you them right now. So you have already seen that the set of all real value functions is a vector space. But then if you use the same vector function addition and function scalar multiplication, then the set of continuous functions is also a vector space. The sum of two continuous functions is continuous. The scalar multiple of a continuous function is continuous. That's Calc 1. If you take the set of all differentiable functions, it's a vector space because the sum of two differentiable functions is differentiable. The constant multiple of a differentiable function is differentiable. That's Calc 1. So D, the set of all differentiable functions, is a subspace of C, the continuous functions, which is a subspace of F, the set of all functions. Then from here, you also get the set of polynomials as a subspace of all these others, and Pn, the set of all polynomials of degree n or less, not exactly n. We know that's not a vector space, but of all polynomials of degree n or less, that we know is indeed a subspace. And by the picture, you can see how they're all kind of contained inside the next larger object. Okay, so then you need something a little more fun. And also this example you're going to see at the end, the very last video. I want to show you that the set of all polynomials of this form is a subspace of P3. So Y is three things. I have to check three things. So the first one is notice this set, which I'll call W, is not empty. And that's because the zero function is in W. So the zero function is the polynomial, which is just always 0 for all x. The second thing is, now let's just take two polynomials in here of this form and add them. So notice that if you take, here is one such polynomial for choice of A and B. And now I need to add another one. Now to add another one, I can't use A and B. So if you add to it something of the same form, we'll say C plus dx plus 2cx squared minus dx cubed. When you add those together, notice you get A plus C plus B plus dx plus 2 times A plus C times x squared minus B plus D x cubed. Now your first thought is, yeah, Professor Dugan, though, that's not that. It doesn't look like that. It should be A, B, C. No, it doesn't have to be. It has to be that form. Notice it certainly has that form because this entry is twice that one. This entry is twice that one. That's fine. And this entry is the opposite of that one. This entry is the opposite of that one. Yeah, that's right. And that is a vector in W. And the third one is do the same thing. So let C be a scalar. Then C times A plus B plus 2ax squared minus bx cubed is written as A times C plus B times C x. And then you have plus 2 times A times C. Notice the way I wrote it. I could write it lots of ways. I chose to write it that way. Times x squared minus B times C. Again, notice how I'm writing it, x cubed. And that is in W. It's in that set because it has the form I needed. It has that this thing is twice that, and this guy is opposite of that. It has the correct form. So then, yeah, this is it. This particular set of all polynomials of this form is a subspace of the set of polynomials of degree 3 or less. Let's try it again. I want to show you that the set of all matrices of this form is a subspace of M22. So then notice, let's just say set W to be this set, this collection of matrices. So obviously W is not equal to the empty set, as the matrix 0, 0, 0, 0 is in that set. So we have that one all math is true. Next, let's just take two things. So then assume, so for A, B, C, and D, notice that A, B, 2A minus B plus C, D, 2C, negative D, that's the sum of two random vectors that are in M22, or at least in this particular set W. But that is equal to A plus C. You get 2 times A plus C. You get B plus D, and you get the opposite of B plus D. Again, you might look at it and go, but that's not the way you described it. The matrix should be A, B, 2A, negative B. No, it just has to have that form. And it does, doesn't it? Notice that this entry is twice that, like it should be. This entry is opposite of that one, which it should be. And that is in W. For A, B, and C, C times AB 2A minus B is equal to AC, BC, 2AC, and the opposite of BC. And that is in W because it has the correct form. So then that shows that this particular collection of matrices of this form is a subspace of the set of all 2x2 matrices, where we're inheriting the vector addition of normal matrix multiplication, normal matrix addition, and we're inheriting the normal scalar multiplication of matrices with scalars. Notice also in the two examples this gave you how incredibly similar they are, even though they are very different objects, polynomials and matrices, and yet the proof was very similar. That's because I'm hinting at a deeper connection between all these things. Hinting or starting to hint at a deeper connection to all these things. All right, one more. So then let's suppose you look at the set of all functions that if you take f of 1, you get 0. That is a subspace. So then y is a subspace of all functions. Proof is very easy. So let's just do that. So notice, and I'll just call this capital W instead. Notice that the function that is always 0 for all x is in W. Of course, if it's equal to 0 for all x, of course it's equal to 0 when I plug in 1 for x. So we now know W is not empty. So W is non-empty. Now let's just pick two things. So suppose I had two functions. I'll call them f and g are in W. Then f of 1 equals 0 and g of 1 equals 0. But then f plus g of 1. Remember the definition of f plus g of 1 is f of 1 plus g of 1. That's the definition of function addition. You've had that definition way back when, but you have not had many opportunities to actually use it. But that's just 0 plus 0, which is 0. So we have then the function f plus g that is in W. Suppose then that f is in W and c is a scalar. Then I know that f of 1 is 0. But then c times f, that function, at 1, by definition, is C of F of 1, because that's how we define matrix multiplication, function of multiplication by scalars. But that is C times 0, and that's 0. So by definition, so C times F is in W. It's therefore a subspace. And that's it. So this weird thing is a subspace of the set of all functions. Okay, so there's one last property you should know, and that is, you might notice that over and over and over again, I keep saying, well, yeah, but all the vectors, I know that there's this one vector that's in the space, and that's because I keep saying 0. Notice that the set's not empty because it has a 0 vector. That's because if you have any subspace at all, it has to contain the 0 vector. It makes sense, it has to. And that 0 vector is the same as the 0 vector for V. They're the exact same object. That's because if you take anything that's in S at all, it's also in V. But the additive inverse of that thing is also in S. So when you add the object and its additive inverse, you have to get the 0 vector. But that's the 0 vector in V. So then that means that if you have any subspace, the 0 vector that's in V, it's also in S. It kind of inherits that 0 vector. That means, though, it's actually kind of easy sometimes to look at a set and go, no, that can't be a subspace. It doesn't have the 0 vector. Like here, this set of objects of matrices, A, 0, B, and A plus 2. The plus 2 is very suspicious. This thing can't be a subspace because it does not contain the 0 vector of M22. Because since the matrix, if A equals 0 and B equals 0, that's the only way that we get the 0 vector, then that matrix would have the form 0, 0, 0, and 2. And that, while that is in the set, that is not the 0 vector. So unfortunately, there's just no way it can be done. There's no way this set of objects contain the 0 vector for V. And I believe that's enough for that particular video.